Okay, so LC oscillators. So we'll start about the classification. Already we have seen in the previous class. Now we'll start with the LC oscillators. First we'll see LC oscillators means there are the two types. One is the Colpitts oscillator, another is the Hartley oscillator. Okay, so only both are same. Only there is some small difference. Okay, so we can go with the two different types of the feedback amplifiers individually. But so since we have the commonality, major commonality between the Hartley and Colpitts oscillator, first we'll derive the common equation which will be applicable for both Hartley and Colpitts. Okay, so then we'll go to the individual Hartley and Colpitts. So now I'm going to derive the general form of LC oscillator. General form of LC oscillator. Okay, general form, which will be in this general form will derive the equation, and that equation will be used to solve Hartley and Colpitts individually. Okay, so for that reason I'm moving to we are deriving the general equation here. So now coming to this general equation, so that is, we know that the feedback block diagram, this is the amplifier here, basic amplifier. Okay, this is the circuit for okay, this is Z1, this is Z2, this is Z3. Okay, so output is taken from here to ground, output is taken across the Z2, so from here to here. Okay, so this is V0, I can tell. Okay, so this is the general form of oscillator. So here the Z1, Z2, Z3 are the inductors and capacitors, whereas for Colpitts oscillator, for Colpitts, Z1 and Z2 are the capacitors, Z3 is the inductor. Okay, for a Hartley oscillator, Z1, Z2 are the inductors, Z3 is the capacitor. That is only the difference. Okay, the remaining portion is everything is same, right? So for Colpitts oscillator, Z1, Z2 capacitors will replace that Z1, Z2 with the capacitor, Z3 will be the inductor. For Hartley oscillator, Z1, Z2 will be replaced with inductor, Z3 will be replaced with the capacitor. So the only the tank circuit parameters are different, and the rest of the things, everything is same. So for that reason, so we are deriving a general equation which will be applicable for both the Colpitts and oscillator. So once if you have that equation, directly you can substitute in the place of Z1, Z2, Z3 corresponding your types of the oscillator. So if you take the oscillator, you can substitute Z1, Z in the place of Z1, Z2. Like Z1 is nothing but 1 by j omega C1, Z2 is nothing but 1 by j omega C2. That is impedance of the capacitors. Z3 is the j omega L. Like that, you can substitute and you can calculate. You can derive the operating frequency. Okay. So this is the that is the reason we are moving to this general form of LC oscillator. Okay. Now let us move to so this is the reason. So now let us derive the general equation for here. So first of all, let us draw the simplified model for this. Let us draw the simplified model. So that is equal to, okay, so anyway, so amplifier is a C amplifier, no? So I'm replacing the amplifier with H parameter model. So just look at this one. I'm taking simplified H parameter model for our easy calculations. This is H. This is what this is what current gain HFE into IB. HFE into IB. Okay, so this is HIE. Okay. This is H1, Z1, Z2, Z1, Z2, this is Z3. Okay, so this input current is IB here. Okay, this is IB current, and this is IC current. This is I1 current. Okay, I1 current. Here is this is I1. This is I2. Okay, so these are the simplified equations. See, uh, in the place of this one amplifier, I am replacing with this simplified H parameter model, and the remaining portion is same. Okay, the remaining portion is same. So now let us look at this equation simplified version, simplified circuit diagram. Let us write some standard equations, some standard equations I like. So see, the output is taken across Z2. So this is the output voltage. Output is taken across the Z2. So therefore, the first left, let us calculate the equivalent. So the load resistance. The load resistance is nothing but the total. The load resistance is nothing but the total. Now look at this point. Look at this point. Okay. So from here to here, so this is the load. No, so ZL is equal to, I can write ZL equal to, I can write Z2 parallel to Z2 parallel to Z3, Z2 parallel to. So you see Z2, this is Z2 here, okay, and so Z3 is parallel to, from, so parallel means this is the path which is parallel to the, so from here to here, this is the path which is parallel to the Z2. Am I right? So Z2 is connected to this. Let us say this is one. Let us say this is one. This is two. This is three node. Okay. Z2 is connected between node 1 to node 3. Z2 is connected between node 1 to node 3, and the parallel connection is also we have to take from node 1 to node 3. So from here to here we have to take. So Z3, so in series with the parallel combination of these two. In series with the parallel combination of these two here. So Z3 plus Z1 parallel to HI. Any doubts in this equation? Any doubts in this?
So please explain also.
So from node 1, node Z2 is connected between node 1 to node 3, node 1 to node 3. Okay, so this I can, for your easy understanding, that I can redraw the circuit. You can redraw the circuit. Uh, this is HFE. Okay, this is Z2 here. This is Z2. Okay, and from here, Z2, Z3, which is parallel to, again, Z1 HIE. So this is the simplified. I'm just redrawing the circuit here like this. Okay, so this is connected to the ground. So now see, this is Z3. So what is the load? Z2 parallel to Z3 plus this parallel combination. So that's only I wrote it here. Okay, so now simplify this ZL. So if we simplify, what we'll get? Okay, so if we simplify, first let us ZL equal to Z2 parallel to Z3. So Z1 plus Z1 means Z1 HIE by Z1 plus HIE. So carefully understand these equations. Okay, Z3 plus Z1 Z1 HI by Z1 plus HI. Okay, now simplify. Z2 parallel to Z2 parallel to is take LCM of it. So Z3 into Z1 plus HIE plus Z1 HIE divided by Z1 plus HIE. Okay, so here next. So Z1 parallel to multiply inside. So Z1 Z3 plus Z3 HIE plus Z1 HIE divided by Z1 plus HIE. So I'm not doing anything. I'm just simplifying. You multiply this Z3 internally for this the Z3 Z1 plus Z3 HIE plus Z1 Z1 HI. Denominator same. So this is the part. Okay. Now again you so it is parallel to Z2. It is parallel to Z2. So now let us take it out. ZL equal to Z2 into Z1 Z3 plus Z3 HIE plus Z1 HIE divided by Z1 plus HIE, okay, by Z2 plus again Z1 Z3 plus Z3 HIE plus Z1 HIE divided by Z1 plus HIE. Okay, so in the parallel combination, so R1 parallel to R2 means R1 into R2 by R1 plus R2. That's the same formula I'm using, and so Z2 parallel to this term. So I did like this. Okay, so from this again you simplified. You multiply the Z2 internally. You multiply Z2 internally. So Z1, Z2, Z3 plus Z2, Z3, HIE plus Z1, Z2, HIE divided by Z1 plus HIE divided by next take LCM of it. So this is one and LCM is nothing but Z1 plus HI is the LCM multiply. So the cross multiply. So Z1 Z2 plus Z2 HIE plus Z1 Z3 plus the remaining this portion is Z1 Z3 plus Z3 HIE plus Z1 HI. Okay. So this cancel. ZL is equal to the final equation is Z1 Z2 Z3 plus Z2 Z3 HIE plus Z1 Z2 HIE divided by so Z1 Z2 from three terms I can take HI as common plus HI is the common into Z1 plus Z2 plus Z3 plus the left out term is Z1 Z3. So this is the load equation. Okay, any doubts in this derivation? Any doubts?
No, sir.
Okay. Okay, so this is the Z. Now we have to calculate the condition. No, so now let us calculate the voltage. So from this we know that. Okay, so we know that. So what is the condition is A beta must be equal to 1. According to the Bar-Carson criteria, A beta must be 1. So to substitute in this, we should know what is A and what is beta. What is beta. So A is nothing but voltage gain is equal to simplified model minus HFE ZL by HI is the formula. Am I right? So voltage gain is equal to minus HFE ZL by HI. So this to substitute ZL here, so we calculated this much derivation. Okay, so to substitute ZL. So ZL is this. This is the equation for ZL. So now substitute here. Now you substitute. So what will get if you substitute here? What will get? Okay, so you keep it later. Okay? So just is your minus HFE into ZL is nothing but this portion by HI. Okay. Next, beta is equal to what? Beta is equal to what? So beta is nothing but we know that VF by V naught. Am I right? So feedback output by output of the basic amplifier. This is the one. So from this V naught is nothing but so now come back. Where is V naught here? So V naught is taken across Z2. Am I right? V naught is taken across the Z2 and so from look at this portion. So this is V naught. So anyway Z2 is parallel with Z3 plus this parallel combination. So the voltage drop across Z2 is equal to the voltage drop this network. Because both are in parallel connection, the voltage will be same. Voltage across Z2 is equal to voltage drop across this path. Am I right? So here I'm taking, so V naught is equal to, what is the current flowing through this path? What is the current flowing? So I1 is flowing. I1 is flowing. So this, see the current I1 is flowing here through this path. ఇక్కడ నుంచి ఇక్కడ దాకా మీకు I1 current అనేది flow అవుతుంది. Okay, but that is an opposite direction. So that is an opposite. Why? Because the load has to flow like this, but it is coming opposite direction. So I am taking V0 is equal to minus I1 into Z3 plus Z1 parallel to HI. Okay, so this is one. V0 is equal to Z3 plus Z1 parallel to HI. So now simple way. Minus I1 into so this portion already calculated, no? Z3 plus ante ఇది వస్తుంది మీకు, Z3 plus అంటే ఈ portion. So you directly can write it. So Z1 Z3 plus already మీకు calculate చేశారు కదా, Z3 HIE plus Z1 HI divided by Z1 plus HI. Okay, this is output voltage. Okay, this is done. Now coming to the VF. VF and feedback. VF is feedback. So where you are getting the feedback? Feedback path is nothing but so this is nothing but a feedback. This is nothing but like I will read it. So this is the green dotted line portion is the green dotted portion line. So that is the feedback. So in this feedback path, what is impedance? This Z1 parallel to HI. Z1 parallel to HI. This is only the feedback. So because output inch input connect and ide kada. Output inch input connect and so this is the input node. So 3 anedi, this is the common node from output to input. So this is the your feedback. So from this minus I1 into Z1 parallel to HIE. So that is equal to VF is equal to minus I1 into Z1 HIE by Z1 plus HIE. Okay, now substituting beta. Beta equal to VF by V0, that is equal to minus I1 into Z1 HIE by Z1 plus HIE divided by V0 is this move. V0 is minus I1 into Z1 Z3 plus Z3 HIE plus Z1 HIE divided by Z1 plus HIE. Okay, so minus I1 cancel, minus I1 cancel, Z1 plus HI, Z1 plus HI cancel. So beta equal to Z1 HI divided by Z1 Z3 plus Z3 HIE plus Z1 HI. This is beta. Now come back to your formula. So what is that? A beta equal to 1. So what is A? Minus HFE ZL by HIE into beta is this portion. So Z1 HIE by Z1 Z3 plus Z3 HIE plus Z1 HIE equal to 1. Okay, so A value is minus HFE ZL by HIE into beta equal to HIE Z1 HIE by Z1 Z3 plus Z3 HIE plus Z1 HIE equal to 1. So this is the one. Now substitute ZL value here, minus HFE by HIE, keep it aside. So ZL plus forward is the formula ZL. So this is the formula. So now bring and substitute here. Okay, so now bring and substitute. So what will get? Okay, so Z1 Z3 Z1, Z2, Z3 plus Z2, Z3 HIE plus Z1, Z3 HIE. So Z2, Z3, Z1, Z2. Z2 divided by, okay, divided by uh, the denominator is Z1, Z2,
Z1, Z2 plus
Z1, Z2 plus
HIE into
HI into
plus
plus
Z1, Z2,
Z1,
Z3.
Z3, right? Z3 into, so this portion again. So H1 ZI by Z1 Z3 plus Z3 HIE plus Z1 HI equal to 1. Okay. Now, you see this portion and this portion. Okay. If you take Z2 as common here, if you take Z2 as common, every term is Z2 as common. If you take Z2 separate, if you write it separately, so what you'll get, I'm writing Z2 here separately. So because Z2 will be missed here, Z2 will be missed here, and Z2 will be missed here. Okay. So what will get? So Z1, Z3, Z3 HIE, Z1 HIE, same, right? So this portion cancel. This portion and that portion cancel. So finally minus HFE Z2 Z2 into Z1 HI. So Z1 Z2 HIE divided by what will get HIE HIE. So okay, so HIE and HIE just cancel. Okay. So this cancel. So finally Z1 Z2 plus HIE into Z1 Z2 Z3 plus Am I audible now? Hello?
Yes, sir.
Anyone
Yes, sir.
Yes.
Is my screen visible to all of you?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So this is the equation. So final, this is the general form equation. So this is you have to remember. Why? Because if the SW examination and all, if you have the question on the Colpitt's oscillator and the Hartley oscillator, you have to start with this equation. Okay, you have to start with this equation. So you have to write the general form for LC oscillator is this, and here the where Z1 Z2 is equal so and so and Z3 is so and so. So then you can substitute here and you can derive the rest of the things. Okay, you have to start this with this equation. So whatever I told, that derivation part, it's not so important, and like so it will not come into the examination. So point of view are, so just to understand the concept of this and how we calculated this general form. Okay, so with respect, if you want to concentrate on SW, this is not so important, but you have to remember this equation at the final equation. Why? Because definitely we'll get the question on Colpitt's or Hartley oscillator. So for those things, you have to start with okay, you have to remember this equation. Is it clear? So now coming to so this is the general form equation for both which is applicable for both the Colpitt's and Hartley oscillators. So now let us come into now let's start with LC oscillators. Now start with LC oscillators here. LC oscillator. Okay, so in the LC oscillator, why it is named as LC oscillator? So why it is named as LC oscillator means nothing but so the tank circuit is designed with inductor and capacitor here. So the inductor and capacitor, hence it is named as the LC oscillator. And one more thing is, and this is the high frequency oscillators. LC oscillator is the high frequency oscillator. So let us see how the signal generated in the LC oscillator. Let us see. So this is LC capacitor and this is inductor. Okay, this is connector ground. This is VCC. Okay, so you see the voltage, the waveforms across the inductor and capacitor is always out of phase. The waveforms in phase, if both are in parallel, the current and current waveforms or voltage waveforms is always opposite, out of phase. So for example, if you apply the VCC sudden as at 12 volts, so capacitor will not charge, it will not entertain the sudden change. So capacitor acts for the short circuit for sudden change in the voltage, sudden change in the voltage. So initially the amplitude, so this flux, so the that inductor stores the current and inductor stores the current, and so due to the flux B, so that current will generate like this. So initially, so that is initially rise. Okay, it will initially rise. Okay, so next after it reaching to the maximum level again it starts to discharge, it will come down. Okay, and so it will coming like this. So you remember one thing, if the inductor is charging, so the capacitor means that discharging. Okay, inductor charging means the capacitor is discharging. So once it is completely charged, it will discharge to capacitor only, it will discharge to capacitor. So now capacitor slowly, so it is discharging now, it is discharging means slowly charging like this. Okay, so and keep on again discharging till to this point, and it will charge till to this point. Again the inductor start to charging inductor, so after capacitor reach to the maximum level, again the capacitor start to discharge, so that will discharge to the again inductor, so it will come down like this. So if you see that waveforms across the inductor and capacitor is always out of phase, so so like this it gives the 180 degrees phase shift. So if it is 180 degrees phase shift and a C amplifier is giving already 180 degrees phase shift, and the total phase shift will be 0 degrees or 360 degrees. So this LC oscillator like this, it satisfies the first Barkhasan criteria. First Barkhasan criteria. And what is the second Barkhasan criteria? Loop gain must be in unity. So A beta is equal to 1 unity. So based on that formula only we derived this equation. Based on that only we derived this equation. So if you are using this equation as a general form, so indirectly you are satisfying that A beta is equal to 1 also. Directly you are satisfying that A beta is equal to 1 also. So this is the LC oscillator here. Okay, so fine. Now let us coming to 1 minute. Okay, let's come to see if somewhere, if at any point of time, so due to internet connection, if you are unable to hear my voice, please let me know or please text me. So through Teams or through WhatsApp, please let me know. If you are unable to listen noise at any time, so due to network issues. Okay, so like this LC oscillator, like it is generating the sinusoidal and it is giving that 180 degrees phase shift. Okay, now let us start with first. Let us start with the Hartley oscillator. Hartley oscillator. Okay, the circuit is okay. This is the circuit of Hartley oscillator. Okay, so in this circuit, R1, R2, RC, RE provides the voltage divider bias network, and coupling capacitors used to block the DC, and bypass capacitor used to avoid the voltage drop across R. So this is what is the general things what we know about the C amplifier. The remaining portion, see, there are the two inductors and one capacitor in the circuit, which will be participate to generate that frequency, operating frequency. Okay, so when the supply voltage plus VCC is switched on, okay, a transient current is produced in the tank circuit and produced in the transient current produced in this tank circuit. That's what I told previously how the LC also generates the oscillator. Okay, so C amplifier is giving 180 and the voltage drop across this inductor. So means between, suppose if it is a first node and the second node and third node, so 1 to 3 is always 180. So this is always 180 here. Okay, so 180 plus 180 gives 360 degrees phase angle. So it gives the 360 degrees phase angle. Okay, so and one more, that is the first criteria of the Barkhasan criteria. And the second point for the Barkhasan criteria is loop gain must be 1, and that's solve this. What we are going to take now. So that is, what is the formula? Barkhasan criteria. Sorry, what is the generalized formula equation? Tell me.
Z1 Z2 plus
Z1.
Z2 plus
Okay.
HIE of
HI of
Z1 plus Z2 plus
Z1
Z3
plus Z plus 3. Okay.
plus Z1 Z3
Plus Z1 Z3
plus HFE into Z1 Z2 equal to 0.
Equal to 0. This is general form. Okay, so this is what a general equation. And otherwise you can take so Z1 Z2 and Z1 Z2 is common. You can redraw the circuit. I mean, you can redraw the equation. Okay, equation is 1 plus HFE into Z1 Z2 equal to 0. Okay, so this is general equation. So HI into Z2 plus Z2 plus Z3 plus Z1 Z3 plus 1 plus HFE into Z1 Z2 equal to 0. This is so where so what is Z1 here? What is Z1? What is Z1? What is Z1? What is Z2? What is Z3? You tell me. What is Z1? Are you hearing me?
Indicators, sir.
Inductors. So since there are the two inductors, I'm taking J omega into L1 plus M, where M is the mutual inductance. Okay. So next Z2 is J omega into L2 plus M, mutual inductance. Z3 is the capacitor, no, 1 by J omega C. These are the Z1, Z2, Z3 values. Am I right? Is it clear? Any doubts in this? Any doubts? Please respond. Any queries? Please respond.
No, sir.
Okay. So now substitute Z1, Z2, Z3 in the equation. You will get HI into Z1 is J omega L1 plus M plus J omega L2 plus M plus 1 by J omega C. So in the place of Z1, Z2, Z3, I substituted all the values J omega into L1 plus M plus J omega L2 plus M plus 1 by J omega C. Okay. Plus Z1. Z1 is J omega L1 plus M into Z3 is 1 by J omega C plus 1 plus HFE into Z1 Z2 అంటే J omega L1 plus M in, okay, Z1 plus J omega into L. So Z2 is again J omega into L2 plus M equal to 0. Now from this HIE into, from this take J omega is common, J omega is common, you will get L1 plus L2 plus 2M. Okay, so you take J omega as common from this term and this term, so you'll get J omega L1 plus L2 plus 2M, M plus M plus 1 by J omega C. Okay, J omega C plus, so from next term the J omega cancel, L1 plus M by C plus 1 plus H of E. So J omega into J omega, so J square omega square, so you'll get omega square. So J square value is, J square is, what is J square?
Minus 1.
Minus ante, so this becomes minus into L1 plus omega, sorry, L1 plus M into L2 plus M equal to 0. So from this now separate all the terms, part, real part and imaginary part. So this is imaginary part. Why? Because J is there. Okay, so this I can write it as HIE. I can write it as HIE. J common this same avutundi. So you will get omega into L1 plus L2 plus 2M minus 1 by omega C. Because 1 by J is nothing but minus J. That J I have taken it common. Okay, so this is imaginary part. Imaginary part. This is imaginary. Okay, the real part is plus L1 plus M by C. Okay, real part is plus L1 plus M by C minus 1 plus HFE into omega square L1 plus M into L2 plus M equal to 0. So this is what real part. Okay, so to calculate operating frequency or resonant frequency, resonant frequency. So make imaginary part equal to 0. Okay, to calculate operating frequency, make imaginary part equal to 0. So take only imaginary part and that is make it equal to 0. Apply that is equal to 0. So what is imaginary part from this equation? So HIE into omega into L1 plus L2 plus 2M minus 1 by omega C equal to 0. So this is the imaginary part, so that I made it to 0. Okay, so now let us assume that this is equation 1. So complete that one equation 1. So in that equation 1, I am taking only the imaginary part to calculate the operating frequency. So from this I can calculate. So omega into, so this I am writing it as this is L equivalent. Okay, so minus 1 by omega is equal to 0. So I send this HIE to this side, so that becomes 0. Okay, so where L equivalent is equal to L1 plus L2 plus 2M. L equivalent to L1 plus L2 plus 2M. Okay, so from this omega L equivalent equal to 1 by omega C. Okay, so omega square equal to 1 by C into L equivalent. Right, so omega is equal to represent that root side, so it will get 1 by C into L equivalent, where omega is nothing but what? 2 pi f. 2 pi f equal to 1 by root C L equivalent. So finally f is equal to 1 by 2 pi root C into L equivalent. This is the frequency. Okay, so this is the frequency for Hartley oscillator. So 1 by 2 pi under root C into L equivalent, where L equivalent is equal to L1 plus L2 plus 2M. Okay, next. And next, this is the oscillation. Next, to calculate condition for sustained oscillations. Okay, sustained oscillations. To calculate, okay, sustained oscillations, make real part equal to 0. This is the condition for sustained oscillations. And I told there is a loop gain, effect of loop gain on the gain ante a beta greater than 1 unte emuntundi, less than
A beta equal to 1.
equal to emunte cheppanu. Sustained oscillations ani cheppanu akkada equal to 1 untali. So to get the sustained oscillations, what would be the condition for this Hartley oscillator? So the real part, take real part, and that is equal to 0. So what is the real part here? Real part is this one, and this is L1 plus by C minus Ishan. Okay, L C minus plus HFE. What is the remaining equation? Okay, equation omega square. Okay, L1 plus M into L2 plus M equal to 0. This is the real part, that is equal to 0. So from this, I can write L1 plus M by C equal to 1 plus HFE into omega square into L1 plus M into L2 plus M. So this minus becomes positive, so that I'm sending it to the cell RH side, it becomes positive. So L1 plus M cancel. So 1 by C equal to 1 plus HFE into omega square is what? What is omega square? This is omega square. Okay, 1 by C into L equivalent. So substitute here 1 by C into L equivalent. Okay, L2 plus M. So okay, C cancel, C cancel. So L equivalent equal to 1 L. So you multiply internally. So L2 plus M plus HFE into L2 plus M. Ela రాస్తున్నాను నేను. Okay, so 1 into L2 plus M, L2 plus M, HFE into L2 plus M, HFE into L2 plus M. So now L equivalent is what? L1 plus L2 plus 2M is equal to L2 plus M plus HFE L2 plus M. So from this L2 L2 cancel, 2M minus M. So it becomes 1. So L1 plus M equal to HFE into L2 plus M. So finally HFE equal to L1 plus M by L2 plus M. This is the condition for sustained oscillations of Hartley oscillator. This is the condition for sustained oscillations for RC oscillator. Okay, so HFE and beta value. So the transistor they are using in Hartley oscillator, that value should be the ratio of L1 plus M by L2 plus M. Okay, so మీరు L1 L2 values ఏదైతే తీసుకుంటారో the transistor, assume that L1 is equal to, for example, L1 is equal to 50 millihenries, L2 is equal to 2 millihenries. So 50 by 2 ఎంత అవుతుంది? 25 milli cancel, so units also 25. So HFE value should be greater than or equal to 25. That is the meaning of this equation. L1 మీరు 50 milli తీసుకొని L2 2 milli తీసుకుంటే, okay, so 50 by 2 అంటే you will get 25. So the value of HFE అంటే the value of the beta of the transistor, ఆ transistor యొక్క beta value should be greater than or equal to 25. Then only that oscillator will generate the sustained oscillations. This is the condition. Okay. For example, note, if there is no mutual inductance, that is M is equal to 0, then the equations rewrote F is equal to 1 by 2 pi under root C into L equivalent, where L equivalent is equal to L1 plus L2 only. So why? Because M is equal to 0, no, that 2M becomes 0. And similarly HF equal to L1 plus L2. Okay, if they suppose if it is there in the problems in the numericals, if they given M value, mutual inductance is equal so and so, you have to take this formula, HFE formula, and frequency is equal 1 by 2 pi root C into L equivalent, where L equivalent equal to L1 plus L2 plus 2M. If M is given, if M is not given in the problem, assume that is 0. Assume that the mutual inductance is 0. If the mutual is not given in that question, assume that is 0. If it is given, you take you substitute whatever the value is given and they calculate. Okay. Understood? Any doubts in this?
No, sir.
Any queries? Any queries? Respond, please.
No,
Are you there?
no, sir.
మీరు అట్లా మాట్లాడుకుంటుంటే అసలు నాకు నా ఆడియో మీకు వస్తుందా లేదా అని నాకు డౌట్ వస్తుంది కదా. Any doubts?
No, sir.
No, sir.
No, sir.
No, sir.
No, sir.
No, sir.
Okay, shall I move to the next topic?
Yes, sir.
Okay. The next one is Colpitt's oscillator. Colpitt's oscillator. Okay. So in this Colpitt's oscillator, the same circuit, only difference is they replace the inductors with capacitors, capacitors with inductors. In the tank circuit, capacitors inductors అంటే ఈ కెపాసిటర్ తీసేసి ఇండక్టర్స్ పెట్టొద్దు. ఇవన్నీ సర్క్యూట్ సి యాంప్లిఫైర్ ఉన్న కెపాసిటర్స్ ఇవన్నీ. ఓకే. C1, C2, L, where Z1 is equal to 1 by j omega C1, Z2 is equal to 1 by j omega C2, Z3 is equal to j omega L. Only one inductance is there, no, so there is no mutual inductance, only inductance. Okay, so note down. Over. Now you can start. You can
Yes, sir.
Go. What is the formula now? General equation formula ఏంటి?
Z1, Z2.
Okay. HI plus Z1, HI into Z1 plus Z2 plus Z3 plus
Z1, Z3.
plus, sorry,
Z1, Z2 of H1 plus HFE.
yes, equal to 0. This is the general equation, right? Now substitute. What is Z1, what is Z2, what is Z3? Okay, after substituting, separate imaginary part and separate real part. Make it imaginary part equal to 0, you will get frequency. And make it real part equal to 0, you will get condition for sustained oscillations. Same procedure. Simple derivation. So only thing is you have to remember this equation. Equation గుర్తుంచుకోవాలి. Okay, you substitute what is Z1, what is Z2, what is Z3, and separate imaginary part and separate real part. So make it imaginary part equal to 0, you will get the frequency. Make it real part equal to 0, you will get the what we call so condition for sustained oscillations. That's it. So substitute HIE 1 by j omega C1 plus 1 by j omega C2 plus j omega L here plus 1 by j omega C1 into j omega L plus 1 plus HFE into 1 by j omega C1 into 1 by j omega C2 equal to 0. Okay. So now hi into 1 by j omega c, I can write minus j by omega c1 minus j by omega c2 plus j omega l plus j omega cancel here, l by c1 plus so j into j becomes j square. Okay, so j square is minus 1, so I can write minus 1 plus hfe into 1 by omega square c1 c2 equal to 0. Okay, so now take j as common here, j into hie minus 1 by omega c1 minus 1 by omega c2 plus omega l plus omega l plus l by c1 minus 1 plus hfe into 1 by omega square c1 c2 equal to 0. Okay, right. So now what is the imaginary part? So this is the imaginary part, imaginary, this is the real part. Okay, so imaginary and real, so make it imaginary equal to 0. So we will get hie into minus 1 by omega c1 minus 1 by omega c2 plus omega l equal to 0. Okay, so that we are making imaginary equal to 0. So from this hi is on that side, it becomes minus 1 by omega c1 minus 1 by omega c2 plus omega l equal to 0. Okay, so next omega l equal to 1 by omega c1 plus 1 by omega c2, that is equal to omega l, and take 1 by omega as common, 1 by c1 plus 1 by c2. Okay, so omega l equal to 1 by omega, in the place of 1 by c1 plus 1 by c2 I can substitute 1 by c equivalent, 1 by c equivalent, 1 by c equivalent equal to 1 by c1 plus 1 by c2. So omega square equal to 1 by l into c equivalent. Okay, so next omega equal to 1 by root l into c equivalent. Okay, so 2 pi f equal to 1 by root l into c equivalent. So finally f is equal to 1 by 2 pi root l into c equivalent. This is the equation, and where c equivalent is equal to c1 c2 by c1 plus c2. C equivalent equal to c1 c2 by c1 plus c2. So this is the formula. Okay, this is the condition for sustained oscillation. Sorry, this is the condition. So this is a frequency, and the condition for sustained oscillations is make real part equal to 0. What is the leftover real part? So L by C1 minus 1 plus HFE into 1 by omega square C1 C2 equal to 0. This is the real part. Now L by C1 equal to 1 plus HFE into 1 by omega square C1 C2. Okay, that is equal to L by C1 into 1 equal to 1 plus HFE into 1 by omega square is what? So this is omega square, right? So omega square is this. So 1 by omega square ante L into C equivalent. L into C equivalent. So here I can write L into C equivalent by C1 C2. C1 C2. Okay. So L will cancel. So 1 by C1 C1 cancel. C1 C1 cancel. So what will get? Okay, what will get? So C2 equal to 1 plus HFE into C equivalent, where C equivalent is C1 C2 by C1 plus C2, right? C equivalent is equal to what? So C1 C2 by C1 plus C2. So this is C1. So C2 C2 cancel. C2 C2 cancel. So C1 plus cross multiply C1 C2 equal to 1 plus HFE into C1. This is left over. So C1 plus C2 equal to multiply C1 plus HFE into C1. Cancel. So finally HFE equal to C2 by C1. Okay. Condition is HFE equal to C2 by C1. So it means what? Whatever the values you are taking in the place of C1, C2, that ratio, that what is that, you will get some value, no? That HFE value should be greater than that ratio value. So then only that Colpitt's oscillator will generate the oscillations. And only it will generate the oscillations. Okay. Any doubts in this?
No, sir.
Okay. Okay. So now the time is 10:25. Okay, I will go with the next topic. Okay, so the next topic is RC oscillators. RC oscillators. Okay, so in this RC oscillator, there are the two types. One is RC phase shift oscillator, and second one is Weyl bridge oscillator. Okay, so RC phase shift. See, RC oscillator means the tank circuit are designed using the resistor and capacitor So hence it named as the RC oscillators. In RC oscillator, there are the two types, and RC phase shift oscillator. Second one is the Wien bridge oscillator. So these two are the low frequency oscillators. These two are the low frequency oscillators. Okay. Uh, so coming to this RC phase shift oscillator, first let us take the heading RC phase shift oscillator. Okay, the circuit is okay. So this is the equation here. Sorry, this is the circuit. Now coming to the circuit diagram. So coming to the circuit diagram, see here we are using three RC networks. Three RC networks here. So one is 1, 2, and 3. Okay. So these three RC networks, each RC network produces the 60 degrees phase angle, and therefore, so overall will becomes till to this point it will gives 180 degrees, and this C amplifier give 180 degrees, total 360 degrees or 0 degrees phase shift. Okay, so this is how we will get. So now we can have that. So why we are using the three RC phase shift network, three RC networks? Can't we generate this 180 degrees using the single RC network? Is the formula is that the theta is equal to tan inverse of 1 by omega RC. Actually, it's a tan inverse of imaginary part by real part. Imaginary into 1 by omega C by R. So it becomes 1 by omega RC. If you want to generate, so 180 degrees using single RC network, and so that becomes tan theta is equal to 1 by omega RC. That implies, so if we take 180 degrees single RC and time of the theta is 180. Tan 180 is, what is the tan 180 value? So infinity value. Am I right? Sorry, sorry. This is a tan 180 is 0. 0 degrees equal to 1 by omega RC. So from this you can write 1 equal to 0. So which is impossible practically. So right, impossible. It's not correct actually. Okay, so this is not correct, right? Not exist. We can say that now it exists. So we can't generate 180 degrees phase shift using single RC network. So let us assume that two RC networks. If you take two RC network, tan theta is equal to 1 by omega RC. So theta becomes 90 degrees. So because two RC networks here generating no, so 90 plus 90 becomes 180. So tan 90. So tan 90 is equal to, so infinity. So infinity is equal to 1 by omega RC. So infinity is 1 by 0 equal to 1 by omega RC here. So from this you can write, from this omega RC equal to 0. Okay. So omega RC equal to, sir? To 0. See, in omega is equal to 0 equal to 0. So the product of three terms, 1, 2, 3. See, if any one of it is 0, then we can say we can satisfy this condition. Therefore, we can generate the 90 using two RC networks. We can generate the 90. But we practically we cannot to satisfy this condition. Why? Because anyway, omega is not equal to 0. Omega not equal to 0 means why? Because if omega is equal to 0, okay, so omega is 0 is nothing but 2 pi f. F is equal to 0. So f is equal to 0 and 10 that is a DC signal. But what we are trying for this RC phase shift oscillator, we are trying for the AC. What is the definition? It gives AC output signal. It gives AC output signal. If you assume that omega is equal to 0, so f is equal to 0, so that is a DC signal. So it's not the signal what we required. Okay, so omega is not equal to 0. Leave it. If you make it resistance equal to 0, if you make it resistance 0, so everything will be replaced by short circuit here. So here replaced by the short circuit. So the voltage drop across the short circuit only are fed back to the input. Here fed back into the input is the voltage drop across this short circuit only. So the voltage drop across the short circuit is what? That is 0 volts. So output will be 0. So if you make R is equal to 0, output is equal to 0. So you will not get output waveform. So R is also not equal to 0. And similarly, capacitor is also not equal to 0. Why? Because if you capacitor make it 0, so the output will be distorted. Okay, so because the capacity is used to block the DC signal, but the DC is not added to the output, so it is not equal to 0. So capacity equal to 0 here. Okay, so not equal to 0. So this is not satisfied. So if you take a 3 RC networks, each angle theta is equal to 60 degrees. So tan theta is equal to 1 by omega RC. So tan theta is root 3 equal to 1 by omega RC here. So omega RC equal to 1 by root 3. So this is one physical quantity. We can take some appropriate combination to set this to satisfy this condition. Yes, we can satisfy this condition. Why? Because 1 by root 3 is of some physical quantity. So you can take some combinations of omega, resistor and capacitor. You can satisfy this condition. So we are going for the 3 RC network. And still you can go for the 4 RC networks also. So then theta is equal to 45 outundi. Okay. So tan theta is equal to 1 by omega RC. So tan 45 is 1 by omega RC. So that is equal to omega RC equal to 1. So this is also physical quantity. You can satisfy, you can by taking some appropriate combinations. Okay. So equal to 1, we can make it not some big issue. Okay. But so you can go with the 5 RC, 6 RC also you can go with. But anyway, I'm comfortable with 3 RC networks. So I'm getting my I'm getting my requirements by taking 3 RC networks. Then why to make my circuit unnecessarily complicated by taking 4 RC, 5 RC, 6 RC like that? So my circuit becomes complicated. So unnecessarily we need not to do add that complexity to my circuit. So I'm going with only 3 RC networks. Okay, so this is the background of the RC phase shift oscillator. Why we are using 3 RC networks. Okay, so now let us coming to the point. Let's coming to the point here. Okay, now redraw the circuit, simplified circuit of a simplified version. So replace that transistor with H parameter model, simplified version. Okay, so now redraw the circuit. This is RC, HFE IB, HIE, IB current. R3 where R is equal to 2 plus HI. Okay, now let's see the circuit. Okay, so this is circuit in the place of here C amplifier. In the place of C amplifier, we replace with a simplified H parameter model. So that is the simplified H parameter model. Okay, so next RC. So RC is connected from collector to ground. This VCC is ground now. So this is connected to ground. So RC will come collector to ground, and the three RC networks I'm drawing same. Okay, so asterisk draw చేస్తున్నాను. So this is RC. Okay, so as resistance ఏం చేస్తున్నా చూడండి ఇక్కడ last resistance is connected to the input. So the total resistance HIE R3 కలిపి నేను R resistance. So here I can redraw the circuit again. So HIE, HFE, IB, RC, capacitor. Okay, C, resistor, and this is RC, where this RC is equal to R3 plus HI. మొత్తం కలిపి resistor, ఈ 3 resistors same, 3 capacitors same, and the RC same. Okay, right? So this is what so my circuit. Now we have to calculate the frequency and condition for sustained oscillator. See, RC is parallel with the current source. This is the current source, and this RC is parallel. Apply the source transformation theorem and convert to the voltage. Why? Because so we know the voltage gains, not current gains. So voltage gain and output voltage, we know that. Further, what voltage source? So minus plus. Why? Because the direction is this. Okay, it is coming down. Okay, it is coming down. So HFE IB. 1 minute. Madam. ఈ క్లాస్ లో ఉంది మేడం 10:50కి అయిపోద్ది వచ్చేస్తాం మేడం ఒక 10 minutes. So RC is parallel now, that goes to the series. So now we have to multiply with RC. Am I right? So now it goes to the parallel. So this is one resistor, and so this resistor is going to the series. That's it. That is only the difference. The remaining part is same. The capacitor. Okay, so the resistor here. Okay, so this is RC. So to relate this feedback resistor into a tank circuit, I'm just taking RC is equal to KR. I'm assuming that some ratio RC is equal to KR. So to relate that characteristics to the feedback resistor. Okay, so the final circuit is this. The final circuit is the simplified version, HFE IB into RC. Okay, so RC go to the series. So to relate that RC and R, I took RC equal to KR, and the remaining RC networks are same. Now this is loop 1, loop 2, loop 3. Okay, so now let us see. This is I1 current, this is I2 current, and this is what I3 current. Okay, so I3 current here. Then what you can write it as okay. You can have the what we call direct. You can write the debt matrix here. So I'm going to calculate the debt of it. So from that I will get some equation. So once the equation obtained, Then what is our procedure? Separate imaginary part, make it 0, you will get the frequency. Separate the real part, make it 0, you will get the condition for sustained oscillation. That procedure is same. Okay, and remember one thing here. Remember one thing. This first loop. Okay. See, the last one is, see this current equation. This is the third loop. This is loop 3. E is in series with this. So what is the IB? So means you can write I3 is equal to IB. Okay. So whatever the current you are taking. So here I3 is nothing but IB. Why? Because the third loop only you are getting fed back to the input. Third loop the input keltundi. So the current will be series. So the resistors are in series. So the current will be same. So I3 is equal to IB here. I3 equal to IB. So therefore you can change this IB like I3. Even you can change I3 like I3 here. Okay, so I3. So now coming to the write the det matrix here directly. Det matrix. Do you know how to write it the det matrix directly from the equations? తెలుసా మీకు?
No, sir.
Yes or no?
No, sir.
తెలీదా మీకు? నేను I will Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. తెలుసా? Z11 is the overall impedance in loop 1. Z12 is common portion between loop 1 and loop 2. Z13 is common portion between loop 1 to loop 3. Similarly, Z21 common portion between loop 2 to loop 1. Like this is there. I think BWL ఎక్కడ వచ్చి ఉండాలి ఇది. No?
No, sir.
Yes or no?
No, sir.
Okay. Leave it. I will tell you. Z1 అంటే ఫస్ట్ లూప్ లో ఉన్న టోటల్ ఇంపిడెన్స్. ఫస్ట్ లూప్ లో ఉన్న టోటల్ ఇంపిడెన్స్. సో now first loop, this is the loop 1. This is the loop 1. So anyway it became I3 term. Okay, so this is not part of your loop 1. This is I3 term కాబట్టి సో థర్డ్ లూప్ టర్మ్ ఇది. ఓకే, లీవ్ ఇట్. సో ఇప్పుడు మీకు ఈ లూప్ లో ఉన్న రిమైనింగ్ ఇంపిడెన్స్ ఎంత ఉంది? ఆర్సీ ఉంది, రెసిస్టర్ ఒకటి ఉంది. am I right? ఆర్సీ, కెపాసిటర్, ద రెసిస్టర్, ఈ 3 టర్మ్స్ ఉన్నాయి. అంతేనా? ఫస్ట్ లూప్ లో టచ్ అయ్యేది ఆర్సీ, రెసిస్టర్, కెపాసిటర్ అండ్ దిస్ రెసిస్టర్. Okay, so this Z we can write it in place of Z11. Z11. So KR, RC అంటే KR plus R plus 1 by J omega C. This is Z11. చూడండి, Z1 అంటే ఇది I3 టర్మ్, ఇది తీసేయండి. ఇది IB is nothing replaced by I3 కదా. సో లీవ్ ఇట్. ఓకే, సో ఇంకేమున్నాయి? RC టర్మ్, RC అంటే KR plus 1 by J omega C plus R. సో అదే నేను ఇక్కడ రాశాను. ఓకే, నెక్స్ట్ Z12 ఫస్ట్ లూప్ కి సెకండ్ లూప్ కి కామన్ గా ఏముంది ఇక్కడ? ఫస్ట్ లూప్ కి సెకండ్ లూప్ కి కామన్ ప్రాపర్టీ ఏముంది?
Resistor.
Sorry,
Resistor. R.
that common property you have to write it as minus negative. Common property negative గా రాయాలి. ఓకే, నెక్స్ట్ ఫస్ట్ లూప్ కి థర్డ్ లూప్ కి Z13 అంటే ఫస్ట్ అండ్ థర్డ్. ఫస్ట్ కి థర్డ్ కి కామన్ ప్రాపర్టీ ఏముంది?
I3 current.
సో I3 కరెంట్, దిస్ ఇస్ I3 కరెంట్ నో. ఓకే, ఇది మీరు అక్కడ ఆపోజిట్ రాయాలి. HFE RC అంటే KR. ఓకే, యాక్చువల్లీ ఇక్కడ మైనస్ ఉండాలి, బట్ సీ ద డైరెక్షన్, కరెంట్ డైరెక్షన్. ఇది ప్లస్, ఇది మైనస్ అయితే విల్ గెట్ పాజిటివ్, బట్ సీ ద డైరెక్షన్ పొలారిటీ చూడండి. యాక్చువల్గా మన ప్లస్ మైనస్ ఉండాలి, బట్ ఇక్కడ మైనస్ ప్లస్ ఉంది కాబట్టి దీనికి ఆల్రెడీ మైనస్ ఉంటుంది. సో మైనస్ ఆఫ్ మైనస్ ప్లస్. ఓకే, ఫర్ దట్ రీజన్ ఐఎమ్ నాట్ రైటింగ్ నెగటివ్ హియర్. ఓకే, సో దిస్ ఇస్ పాజిటివ్. ఓకే, నెక్స్ట్ 2 అని చెప్పండి. సెకండ్ లూప్ కి ఫస్ట్ లూప్ కి కామన్ ప్రాపర్టీ ఏంది? సెకండ్ కి ఫస్ట్ కి
Resistors.
resistors only. So that is R. Next 2 2. సెకండ్ లూప్ లో టోటల్ ఏముంది? టోటల్ రెసిస్టెన్స్ ఏమున్నాయి అసలు? ఏం కాంపోనెంట్స్ ఉంది సెకండ్ లూప్ కి?
Resistor, capacitor, resistor.
సో 2 రెసిస్టర్స్ ఉన్నాయి, ఒక కెపాసిటర్ ఉంది. సో రెసిస్టర్ ప్లస్ రెసిస్టర్ 2R plus 1/j⍵c. Am I right? Okay, next.
Yes, sir.
Next. So సెకండ్ కి థర్డ్ కి కామన్ ప్రాపర్టీ ఉంది, సెకండ్ లూప్ కి థర్డ్ లూప్ కి?
R.
So that is R. Okay. థర్డ్ లూప్ కి ఫస్ట్ లూప్ కి ఏం కామన్ ఉంది? థర్డ్ లూప్.
I3.
Okay, see, third loop ki first loop ki there is no connection. I3 term is there in the I1, but I1 is not there in I3. So see the logic. I3 term make I1 loop lo undi gaani I1 current anedi I3 loop lo le. Am I right? So there is no common properties, 0. Third ki second ki, third ki second ki emundi? Resistor minus R. The third loop total ఏముంది? ఓన్లీ థర్డ్ లూప్. టోటల్ ఇంపెడెన్స్ ఇన్ థర్డ్ లూప్.
Resistors, 1 capacitor. 2R.
Yes, 2R plus
1/j.
equal to 0. This is dead. Now you calculate that, you will get the condition. Separate imaginary part, separate real part, and calculate. Okay, and the debt మీరు ఎట్లా క్యాలిక్యులేట్ చేస్తారు? ఎలా చేస్తారు? Even you calculate like this or like this. Am I right? Yes or no? So debt
Yes,
will be
sir.
same. మీరు వర్టికల్ చేసినా మీకు డెట్ అనేది సేమ్ ఉంటుంది. ఈవెన్ మీరు ఫస్ట్ రో, సెకండ్ రో చేయొచ్చు, థర్డ్ రో చేయొచ్చు, ఏ రో అంటే ఎనీ కాలం ఆర్ ఎనీ రో యూ కెన్ డూ ఇట్. బట్